Good morning, everyone, and welcome to our seminar, our hydraulic fraction community seminar. Today, it is my great pleasure to introduce our speaker, Carlo Peruzzo. He's based in Italy. And so Carlo received his bachelor and master's degree in civil engineering from University of Padua. And then he did PhD at APFL in Switzerland, and where he also did a short postdoc there. And just on November 1st, just yesterday, he became my colleague and joined ResFrac. And today, again, he's going to speak about the interaction of a hydraulic fracture with a repetitive sequence of multiple layers of different fracture toughness. Okay, Carlo, so the floor is yours. Go ahead.
Well, thanks, Igor, for the kind interaction. So I start with this with a picture, an outcrop that I took myself in Aberystwyth in UK, where you can see here my driving license card actually size, and behind a beautiful sequence of layers, of different layers with different properties. And we're gonna try to answer to this question: what's the interaction of hydraulic fracture? Starting from strong assumptions and trying to relaxing them. So I just put it out that we were going to assume that the fluid that we're going to inject in the subsurface will be such that the fracture will always propagate on a plane, because we want to understand what's or evaluate or estimate the maximum height growth that we can reach. And to do that, we kind of need this assumption. Then I have another outcrop, since you are in the US, so this is at a larger scale actually, since always with layers, different fracture toughness. Hopefully, we know that in the subsurface the main reason why a fracture gets contained is the confining stress, but here we will address this toughness difference. So looking in the literature, Senseni in 1984 actually published this data where for 3 different wellbores of the Pisans Basin, he actually measured fracture toughness with depth. And it's very nice because we have an example of how fracture toughness is changing, is varying with depth. You see here megapascal, 0.5 to 3. And it's still at lab scale measurement. This is not like for large scale measurement, but the samples are pretty small. So that's the only published results I found. Then being that the ratio of the maximum and the minimum fracture toughness you can find here for different lithologies is between 1 and 5. I looked in people that studied the fracture toughness in the lab, and good studies actually shows for the same lithology, for instance, sandstone and different rock units, so different kind of sandstone picked up from these sort of different places. That's arbitrary, but that's what you can do if you want to have an idea of what could be the ratio of fracture toughness you can find more or less in nature. That's the only thing looking in the literature if you don't find measurement like this. And again, this you show between 1 and 3. That's the ratio between the maximum and the minimum fracture toughness measurements. And these in the table here below, just look at the central column here, the green one. You see studies made by people that considered different lithologies and different rock units as well. And let's say it's in this range between 1, 2, 1, and 5. And this is still lab scale measurements. Now, is it important or not? And how does it affect hydraulic fracture propagation, these measurements? So what is behind the considerations presented here is linear hydraulic fracture mechanics, well established nowadays. We solve in the numerical solver I use here to in the results I will present later, numerical results. We basically solve the 4 equations. Actually, this equation reported here. You have elasticity, which is the relating fluid pressure, confining stress, and opening. It's a boundary integral equation for balance of momentum. Then you have the mass conservation for the fluid, for the Poiseuille and the Poiseuille law for the width average balance of momentum for the fluid. Then you've got the propagation condition, as we know already from previous studies. The dimensionless toughness is, in this case, that there is no leak-off, is the only parameter that controls the propagation of the fractures. Is a dimensionless number that controls its propagation. And these numbers, as you can see, it depends on h. I just put it as the fracture size here, h, for this somewhat radial fracture here. And then you have other numbers, E prime, Q0, the injection rate, mu prime, then you have the viscosity and fracture toughness. So when this parameter is larger than 1, I just recall we are in the K regime. You will hear a lot about it later, toughness-dominated regime. So all the energy is mainly dissipated in the creation of new fracture surfaces. Whereas if this number is less than 1, we are in the viscosity-dominated regime, where all the energy is actually dissipated in the fluid flow. And we can have a direct evidence of that if we consider a power balance for this phenomenon, for an hydraulic fracture propagating, where we have an external power that is provided by the injection. Q0 is injection rate times P, pressure at the injection point. It's balanced by the dissipation that you have in the viscous fluid flow, the energy stored as elastic deformation in the solid medium, and the one dissipated to create new fracture surface. So in the plot below, you can appreciate the purple curve that is the one above all the others, because it's exactly the sum of all the other curves below, and that's the external power, okay, the one that that is entering the system via the injection. And then you can see that when the fracture is small, so when this toughness, dimensionless toughness is actually very little, it's 0.1 here, all the energy, this purple curve is very well approximated, if you like, but it's almost made by this dissipation by viscous fluid flow. Whereas for values of this number above 1, you see that this dissipation in the fluid flow goes to 0, and the one that dominates is really the one creating the new fracture surface. But here in this talk, we are concerned with heterogeneities, and several models have been developed in the past, as you know, to take into account the effect of the heterogeneities on the fracture, on hydraulic fracture shape. I recall the PKN model, KGD model, pseudo 3D is more elaborated, more recent, and the planar 3D model is the one, the most complete one, the one that I've used in comparison with the PKN model. So here we will consider the PKN model and the planar 3D. Why the PKN model? Because when a radial hydraulic fracture starts to grow and then hits the bonding layers, then is actually not able, in the small yielding approximation, is not able to break through a lot, and it stays almost parallel to the theoretically parallel to the bonding layers, and it propagates only in one direction, having an almost elliptical cross section. So the opening profile actually is elliptical, and this is because in this slide we see the planar 3D model compared to the PKN models, I should say now in a moment, and you see that elasticity, this operator is reduces actually to a simple relation relating the fluid pressure to the Young modulus, the fracture height h, your pay zone, and the average fracture opening can be written in this simple way. And this is actually an exact reduction in case the fracture is of L, of length L infinite. But actually we don't have infinite fractures, but that's still a very good approximation that made the success of the PKN model. So here, as you see, we have two models, PKN M and K. Most of you probably know PKN M, and others will know both. PKN M is the classical PKN model, where actually it's so-called viscosity-dominated model, because in the contrary, in the PKN-K model, the viscosity of the fluid is going to be 0. So the mass conservation is similar to the one of the planar 3D model for the case of normal of PKN M fractures, so viscosity-dominated fractures. Whereas in the PKN case, the viscosity is to 0, so the mass conservation is reducing to a balance between a volume balance between what we inject and what is in the fracture. So the length multiplied by the opening and the dimension in the pay zone height. On the other hand, for the propagation condition, in the case of the viscosity dominated, there is no dissipation to the creation of the new fracture surfaces. The fracture toughness is 0, whereas in the pKnK case, we have we say that K1 is equal to K1C, but we also have an expression for the energy release rate, or I should say the stress intensity factor that allowed actually Garagash in 2015 to actually derive a solution, analytical solution for this propagation. You might wonder why this condition where K1 is related in this way to pressure and square root of height, where does it come from? Well, actually, this is coming from, I'm telling you now, it's coming from already an idea of Gille in 1985. Here I just put a screenshot where he's actually considering very elongated surface cracks, not even buried at depth, as you could think of an hydraulic fracture, so even surface cracks, but very elongated in one direction, such that you could compute the energy release rate simply by computing the elastic energy that you store of a unitary advancement of this tunnel-like fracture. So now let's assume that we have an infinite toughness jump. So this is actually a simulation where you see that the fracture does not break through in the bonding layers that are represented with this pink color on very high fracture toughness. And you see that our initial radial fracture touches the interface, and then it gets contained and elongated, and hopefully it will go and will be represented and described by the PKN model. And I want to highlight you the difference between PKNK and PKNM models and how this is relating to a radial crack propagation at the moment it touches the interface. So in the plot here, you see the dimensionless length of the fracture. So in this direction, the length, as a function of time as it grows. You have black lines, they are thin, and they represent the PKN solution in the toughness dominated the PKNK here before actually we reach the transition time, which is at 1, the transition dimensionless time, this is 1 in this horizontal axis, and then you go to the PKNM limiting regime. And you can clearly see that you have a series of simulations. So you see you have a series of radial simulations, and the difference between all these simulations is actually the dimensionless toughness at the moment you touch the interface. In other words, all the different simulations have different dominant energy mechanism at the moment they touch the interface. Here you see that, for instance, here you see this purple curve here is touching at the interface where you have this red dot that I'm covering now and then I'm uncovering, and then is slowly transitioning to a PKNK regime. And this is a toughness-dominated fracture. Dimensional toughness is very high. And surprisingly, also when you touch the interface in viscosity-dominated radial, then you are immediately viscosity-dominated PKNM. So this can be shown that for a radial fracture at the beginning you're viscosity-dominated, but then as the radius grows, you reach a transition length scale, and then you're toughness-dominated at late time. Whereas for the PKN fracture under constant injection rate, that's the opposite. So you start toughness dominated eventually, and then you reach a transition length scale up to the moment in which you switch to a viscosity dominated fracture, where the energy dissipated is actually all in the fluid flow. And why physically is that? It's because you see that the height of the fracture doesn't change, so the dissipation in the creation of the new fractures actually remains constant, whereas the length of this hypothetical pipe or a hypothetical tunnel where the fluid has to go through is increasing with time, and that makes it obviously the late time option for a constant injection rate. So interesting is to have a look at the dimensionless opening, because as you can see here, we are radial. We are radial, so we have this simulation purple one. I'm going to pick up this simulation because it's quite interesting. So we are radial, we approach with a different slope because we are toughness dominated. So we have different slope compared to the other one that I'm highlighting now. And then we turn to the PKNK solution, which is prescribing, it's actually a solution in which the fracture opening is constant throughout throughout the fracture. So is going to be constant, and then if I would have let the simulation going for much longer, then the fracture would have got to a certain length, past the transition length scale that gives this main dissipation energy in the fluid flow, such that the fracture opening will start to increase, and we will follow this peak and increase of the opening. And this opening here is picked up specifically at the injection point, but similarly would be elsewhere. Now, for the pressure, the pressure, as you know, is decreasing the radial case in the radial case, but then as soon as we touch the interface that we are in the PKNK case, then the pressure it remains constant. It doesn't increase, and then once we reach a critical length scale, then it starts to increase again, and that's interesting, and it has interesting implications that we will see throughout all the rest of the presentation. So now I gave for granted that an hydraulic fracture can be stopped by an heterogeneity of fracture energy, but the question, let's say, would be, imagine you're injecting the subsurface and then you're asking yourself, is it the jump in fracture energy or fracture toughness enough to arrest the fracture? So here we have a situation in which we have a double layer, but the answer doesn't really change if you consider a single the presence of a single layer. So the elephant in the room, I just put it out clear, is that we consider a jump in fracture toughness, but for simplicity and to understand better the problem, we keep everything else constant. So notably the Young modulus is constant and sigma naught is constant. In such a way, we can do something analytical. And specifically, by considering the fracture exactly at the moment here where you touch the bonding layers. So when here you have K1C1 is the fracture toughness in the phase zone, then you have your radial fracture at the moment in which you touch the bonding layers, then you can take a cross section here, A prime, and then you see you have a fracture that is about to touch the interface with a given velocity. Well, we can approximate the fracture opening and the behavior of the fracture close to the fracture front with the analytical solution for a steadily moving semi-infinite hydraulic fracture. I will come back to this in a moment, but let's say we can approximate and we can consider this piece of fracture at a given extent from the interface. And now we are going to write an energy balance for the fracture, saying what energy is dissipated in the viscous fluid, what energy is released to the creation of the new fracture surfaces. And then we have the difference between the energy that is coming in the fracture and the one stored elastically in the medium. And then we can couple this energy balance with the propagation condition. So, well, this gives us an enhanced propagation condition that takes into account what are the different ways of dissipating energy that we have into the system. So not only the creation of new fractures, but also the dissipations in the fluid flow. So I'm going a bit fast here. We consider a state when we are before touching the interface, so we can use this enhanced propagation condition, and the state 2 when we actually just touch the interface. So the velocity is actually 0 immediately after I touch the interface, and the second before it was actually larger than 0. The fracture was propagating with whatever velocity. And now, well, I can say that between state 1 and 2, nothing changed. The only thing that changes is this fracture toughness that is changing because of the position of the fracture front. And so what we can do, we can use the analytical solution for the fracture opening for a steadily moving hydraulic fracture. So I report it here. Here we have the fracture front, and as we move far from the fracture front, it's a dimensionless distance. We have an analytical solution for the dimensionless opening, which has been also validated by experiments. Here, when the distance is going to be 0, we recover the classical square root asymptote. Whereas when we go past 1, in this case, it's far after LMK, we recover this 2/3 asymptote for the fracture opening. We need the fracture opening to compute this the integral that is expressed here for the viscous dissipation, to compute it and to obtain something. So we obtain a relationship from this energy balance, if you like, which is actually a function of 2 dimensionless numbers that are actually the nothing new, because these dimensionless numbers are again the ratio between the toughness, the fracture toughness of the two layers, and this is K1C2 over K1C1. And the other dimensionless number is actually the dimensionless toughness of the fracture at the moment we touch the interface. So these two numbers are kind of known. And from this relationship, we can get some analytical estimates in the case in which you have a toughness-dominated radial fracture touching the interface, and in the case in which you have a viscosity-dominated radial fracture touching. And so we have a parametric space now, because as a function of those two dimensionless number, we can define this parametric space, where on the horizontal axis, you have the ratio between the two dissipated energies, and on the vertical axis, you have the ratio between the toughness in the layers. So, and these lines that we found, one is valid, the blue one is valid on the left side of the plot, they are asymptotic values, and the red one is valid on the extreme right part of this plot. These two lines divide the parametric space into parts that are telling us simply that if you are below these two lines, as soon as the fracture reaches the interface, it will break through immediately. Whereas in the other case, if you are in this part, you will have a transient containment. I'm not telling you for how long you will remain contained. That's going to be the next few slides. But here you do have a containment. So I have validated those trends, let's say those asymptotic or estimates, if you want, with the numerical simulations using a full 3D planar hydraulic fracture simulation. Here I have colored the red zone is the one in which I have immediate breakthrough. The green zone is the zone in which I have a transient containment. The red and blue dashed lines are these analytical predictions. They are based on simplifying assumptions. It's a 1D assumption, essentially. But it contains the correct information because the slope is actually confirmed by those points which represents the numerical results. And by the way, the stars are related to the case in which you have two layers, and the cross are related to the case in which you have one single layer. So now we have answered the question when you actually arrest the fracture, but suppose that you are able to transiently contain the fracture. Now the question is, for how long the bonding layers are able to contain our fracture? So to do that, we have to consider an elongated fracture. I show the footprint here, and then we consider the cross section. And in particular, we focus on the stress intensity factor here at the interface with the bonding layers. And for these fractures, we assume, okay, they are long enough. You have already had the transition, the PKN case. And so you know that the fracture opening is going to be elliptical. So the opening as a function of Z is going to be an ellipse, and a function representing an ellipse. And then you have a stress intensity. If you know that your opening profile, then you know actually the stress intensity factor. And you can plug back the expression for the fracture opening, expressing the stress intensity factor only as a function of the opening at the injection point. And this is somehow relevant because look, we know the opening at the injection point, how it evolves as a function of time. We have shown it before. So if you come from the toughness dominated radial, you touch the interface, and then you see after a little transient, your opening remains constant. Whereas if you come from the viscosity dominated case, you touch the interface, your opening increases immediately. So let's focus on the toughness dominated case, where you have this constant time you need to wait before the fracture starts to increase again, the fracture opening. And note that increasing fracture opening again, or having a constant fracture opening, means having a constant stress intensity factor, because stress intensity factor is a function of how the fracture opening evolves. So if we substitute this analytical solution, so this horizontal black line into this equation, then we will obtain a criteria which tells us, hey, if your ratio of toughness between the layers K1C2 over K1C1 is above this critical value of square root of 2, and your hydraulic fracture, your radial hydraulic fracture, the moment it touches the interface was a toughness dominated one, hey, you can establish a pKn-K fracture, so you will be transiently contained, at least for the time it takes the pKn fracture to transition to the pKn-M regime and start to grow again your stress intensity factor. So the full parametric space now, it depends on three-dimensionless number. So we are interested, so this is, I call it dimensionless number. We are interested in the time you stay contained. Then this is a function, as we have seen, of the dimensionless toughness at the time you touch. And as we have seen, is a function of the ratio between the toughness in the two bonding layers. So we expect that this amount of time depends on these dimensionless numbers. Now, there is a red region and the green region. The red region represents the region where you have an immediate breakthrough. The fracture will touch the interface and it will immediately break through. The green region is the region where you can hope for a bit of containment. And for a very large dimensionless toughness here, you see that there is a jump in the function delta TC, which is a jump in the time you need to wait. And why there is this jump, you already probably understood it, because as you have seen here, if you touch the interface in the toughness dominated regime, your opening does not increase. Therefore, your stress intensity factor does not increase, and therefore your fracture does not break through. You have a latency period if you're able to establish this pKn-K. And again, it means that your ratio of fracture toughness needs to be above this special value of 1.41, the square root of the value. So now we have an understanding of for how long a fracture remains contained as a function of the parameters that govern the problem. Again, the assumption here is homogeneous Young modulus, and we assume that the fracture remains planar because we want to have an estimate, an upper bound of what could be the, let's say, the minimum time, let's say, in other words, that the fracture remains contained, or an upper bound for the height growth. Now with this knowledge that we developed so far, we can try to address this somehow more complicated problem of how is the late time hydraulic fracture behavior if we consider a multi-layered material. So what do I mean by multi-layered material? Again, I stress out I consider a distribution of fracture toughness along the vertical direction in this small sketch. I consider all the other properties homogeneous, like homogeneous Young modulus, Poisson ratio, confining stress. We are just interested in trying to understand with solid basis what could be and strong hypothesis also, what could be the behavior of this of the hydraulic fracture propagating in this system. Because maybe most of you are thinking, okay, this fracture will grow somehow in a elliptical way with a fixed aspect ratio. But what I would try to convince you is that there is also a possibility that we will have a so-called late time contained height growth. So now let's try to understand a bit more what is the setup that I've chosen for the simulations I will show you later, and what are the results. So I expect, as I already mentioned, I expect two late time behaviors for the fracture. One behavior is somehow what we would expect. So it's a late time self-similar, if I keep injecting, self-similar propagation with a somehow constant aspect ratio. In other words, if you take the horizontal velocity, v horizontal here, and the vertical velocity here, the ratio between the two will go somehow to a constant at late time. Whereas in the other scenario that it also exists, and I'm going to show you, you have that this ratio between the vertical velocity and the horizontal velocity is going to zero at late time. And this means that you will see a fracture that looks like a finger. The more time you inject, the more the fracture will grow horizontally compared to vertically. And so now we consider, or how I decided to address this problem is to consider a very simple toughness distribution, actually the simplest that I could think of, probably. And I considered the two layers that are repeating and of different fracture toughness, K1C2 and K1C1. K1C2 is the you could think of the higher one. And then we characterize by two different heights, H1 and H2. And this package made of these two layers of different height and different fracture toughness is actually repeating. As you see, it repeats again over and over, ideally infinite times. So now big H denotes not anymore the pay zone, but denotes just this package that repeats, and small h denotes the overall, the large scale fracture height. So now mind that this we are considering here fractures that yes, they grow, they are large scale fracture, but still smaller than the length scale associated to the gravity. In other words, the length scale after which the buoyancy will start to play a role. So the difference between density of the fluid and the confining stress, the gradient of the confining stress in the subsurface. So the elephant in the room again is the Young modulus is constant, but let's have a look at the simulation, how it develops and the repeated pattern that we have. So here we have an initial footprint, a radial footprint already is touching the two bonded layers, not to consume too many elements in a simulation. And then you essentially grow, contain. I assume that K1C2 is sufficiently high to contain the fracture. And then the fracture grows both laterally, but let's say that I'm at the point that it was breaking through, so it starts to break through and eats the vertical, eats vertically the higher toughness layer. And then as soon as it reaches the low toughness layer, the fracture only propagates in this one. It stops propagating horizontally. And then, interestingly, the fracture fills up again with the main front, you see? And we can find it starts to propagate as a wall. So you see that from D to E actually propagates as a single fracture. And this process A to E actually repeats. That's the interesting part that we can use later to make some consideration, because if this was the situation just before breakthrough, now in F, the fracture just propagates in the high toughness region as B. In G, similar to C, is actually propagating in the low toughness region, so it's having the breakthrough in the less tough layer, and then the fracture catches up with the main front, and then it propagates as a wall front until I stopped the simulation because I had too many elements at that point, so it was taking too much time. But essentially, this mechanism repeats. So let's try to do something to estimate. Let's try to estimate something, the ratio between the two velocities. The velocity is vertically and horizontally, but I don't take the time step to be the time from A to B, whereas I just take T to be the just before breakthrough, and then the fracture breaks through over a package of layers, and then I have T plus delta T, which is after it starts to break through into a new package of layers. So now we can estimate the horizontal velocity simply as taking the time t and t plus delta e t. Then we have 2L divided by delta t. Then we estimate the vertical velocity because the fracture between A and E grows vertically. We estimate it at 2h over delta t, and we obtain simply the ratio that v vertical divided by v horizontal is proportional to h, which is the height of the little package that repeats, divided by delta L. So H is very easy. The thing is that how do we estimate delta L? That's the interesting part. So to estimate delta L, well, we know the length at breakthrough at each time. So at this stage A, we know the length at breakthrough because that's a contained fracture here over a homogeneous medium. So what do we do when the fracture is actually propagating over several layers and it's not homogeneous anymore? So we can still think that we know the length LT plus delta T, but in fact, we know it because this problem is homogenizable, as already Jim Rice demonstrated in 1988, providing an equation that essentially expresses the fact that you can consider the system E equal this one below equivalent to the one heterogeneous one, but you need to make sure that the two systems where they're propagating horizontally, they are consuming the same energy. So if that's the case, we can estimate an equivalent fracture toughness for the horizontal propagation. That this was also suggested by Igor recently in a recent paper, and we can use actually this equivalent toughness and leverage the knowledge of the contained fracture bounded by two layers that we had before. So we go back to the question, when does a contained fracture break through? And we go back and we look at the stress intensity factor at the interface with the bonded layers, but knowing that now we have to use the equivalent fracture toughness. As we know from the previous knowledge, the stress intensity factor is constant during the time that I'm propagating in the toughness in the PKN toughness dominated regime. Otherwise, it keeps increasing. So this actually situation in which we have a fracture that remains contained and propagates horizontally until a given length scale where I have this breakthrough, and this is this LKM PKN, which is functional, by the way, of the height of this fracture. So once the fracture will be at a later stage, it will have a higher height. So I can change a little h here in this characteristic length scale. I will obtain another characteristic length scale. So this length scale is increasing as the fracture grows vertically. So to summarize, we are in the case in which the fracture is less than this characteristic length scale, and the toughness ratio between the maximum toughness, the vertical maximum toughness that we have in the system, and the equivalent one is larger than square root of 2. So in this case, we are actually contained. And for and since I know the distribution of fracture toughness vertically, we actually can establish a parametric space where, by simply taking this equivalence, that the ratio must be equivalent to or larger than square root of 2 or smaller, we can establish a parametric space where we have the ratio between the layers' height, the ratio between fracture toughness, and then we have two regions, the green one, where we can have a late time contained height growth because our fracture has grown, and the more the fracture grows through these layers, and the more it goes towards the toughness dominated regime. So late time necessarily you are going to be always toughness dominated in the PKN fracture for a contained PKN fracture. But when the toughness ratio K1C2 divided by K1C equivalent, so this equivalent horizontal propagation is smaller than square root of 2, that this cannot happen. So the fracture will always break through somewhat in the transition between before actually going and being able to propagate as a PKNK, a toughness dominated PKN fracture. And that's why you will have in this case a late time self-similar propagation with a constant aspect ratio. So we can estimate, finally, we can substitute this transition landscape for the green region. So if we are in the green region, we can substitute this transition landscape inside the estimate of vertical versus horizontal velocity, this ratio. And we can express a simple formula here that tells us, okay, as a function of the dimensionless toughness, finally, of the system, now the dimensionless toughness is defined with this K1C equivalent and the height of the current height of your fracture, I can tell you what is the ratio between the vertical and the horizontal velocity. So I've done this and for some real applications, and I have found out that for microhydraulic fracturing tests, I assume the typical values for the parameters, so either small injection rate, 0.1 liter per minute, or higher, let's say 1.5 liter per minute, water as a viscosity, 1 meter of height, it's the height of your current height of the fracture, I assume some small layering, some fine scale layering with not so crazy change in fracture toughness, actually a jump of square root of 2. And you can see that in some cases, the ratio between the vertical to horizontal velocity is 1%, whereas in other cases is higher. So if we consider now hydraulic fracturing treatment, let's have a look just at the first line, maybe for the sake of time. We have, I've taken 360 liter per minute, 1 Pascal per second is the viscosity, a fracture of height, 40 meters, layers that are relatively fine. I would say, well, still almost 1 meter, and then 5 centimeters here. Toughness ratio about square root of 2, not crazy. I mean, these are values that are measured at lab scale. Then maybe you could argue that these values are at hydraulic fracture size of 40 meters may be different, the scale dependence toughness. Well, this is not relevant as it was before, but I would say that one needs to play around with the values of fracture toughness, because here I took relatively small values. So here, if I take 3.5 and 5 for the fracture toughness in the 2 layers, then in the 2 layers repeats as a sequence again, then well, I will obtain that the ratio between the 2 velocities is 30%. And this estimate is valid when it's below 1. Okay, so to sum up the key points here and there, can a toughness jump arrest an hydraulic fracture? Yes. How important a given toughness jump is? Well, it depends. We have seen that it depends on the dimensionless toughness of your fracture, evaluated with the fracture size, age. Will a contained hydraulic fracture always break through? Well, if I keep injecting at a constant rate, of course. So, well, yes, it will always break through. We have seen it because a PKM fracture will always evolve into a PKM fracture where the opening will increase with time. So the stress intensity factor will increase with time, and so I'm gonna have the breakthrough. So finally, I made an estimate of how to compute the ratio between vertical and horizontal velocity, and this estimate is valid when the ratio between this maximum fracture toughness that you have in your system compared to the equivalent one. By equivalent, it's defined at Lagim Rice. So by via this average of with the square of K1C, and also when the horizontal length scale of your fracture is less than the transition one. In other words, where you are propagating in the toughness limited regime. And mind the fact again, then at late time your fracture height is going to grow, and so this transition length scale is going to grow with the height to the square. That's why I can say to you that at late time, if your fracture is going to be contained, if your fracture is going to propagate initially in the viscosity dominated regime or as a viscosity dominated PKM fracture, then at late time it has to go and propagate as a toughness dominated PKM fracture. So in other words, your hydraulic fracture will feel the presence of your layering. Okay, so and to end, I leave you with this nice picture still in UK of an outcrop of a layered, finely layered formation. And here you have a 1.8 meter, 1.7 meter man for scale. And I thank you for your attention.
This is Ali Donashi. I'd like to just make a couple of points for your information. Very nice mathematical work. First of all, I have published more than 50 papers on this subject, and I'm surprised none of them got your attention. But just for your information, the most critical parameter here is the shear strength of the interface. If the shear strength of the interface is low as the hydraulic fracture approaches the interface, and if any shear failure occurs along the interface, that will blunt the tip of the hydraulic fracture, and once the tip of the hydraulic fracture is blunted, it doesn't grow anymore. So as you're looking at this thing, the most critical parameter here is the shear strength of the interface. How strongly bonded are the two formations together? And for low shear strength along the interface, if there is any sliding that happens, no matter how small it is, if the tip of the fracture is blunted, it stops growing. Just for your information.
Yeah, so thanks for the comment. I've seen your papers, and actually I agree with you. I've seen, but here I'm taking let's say a more strong assumption. We want to have an overall estimate. Let's say a worst case estimate. we assume, okay, let's assume that it stays planar. It doesn't. There is no slip between the two. It's like the worst case scenario, in other words. But yeah, of course, if other processes are going on at the interface, then yeah, this has to be checked with I would like to check it like with that would be interesting to check with a 3D planar simulation, because you see that you have this horizontal spreading. But anyway, I agree with your comments.
Okay, well, thank you, Ali Danishi, for providing the critical view. I think it's always very important to be very critical of everything that's been done. So we have a question from chat from Jiha Wang, and so what he asked is that you show the parametric space to determine when the fracture will break through a high toughness layer, but he's wondering if there is a similar study to develop such parametric space when the fracture will break through a high stress layer.
Well, actually, yeah, you mean a study for how long it would be contained? So I have a paper in preparation on that for a fracture that is contained actually by 2 layers with the higher confining stress. And the answer I can already give you, the parametric space is not that different, in fact, because there will be also a situation in which you will be transiently contained for a while. So your stress intensity factor does not increase. It's going to be constant until you reach a critical length scale. And then after you reach this length scale, then you have a vertical growth going on. So there is a similar thing, and it will come out soon, hopefully.
Yeah, just a comment again. I have looked into that situation, and basically, if you have a higher stress, first of all, you need to consider that in reality, you always have a layer above and a below. So you're not just looking at one stress above and one stress below, same stress below. You can have 3 different stresses. And the higher stress slows down the growth of the hydraulic fracture. And if there is a choice between 2 different stresses above and below, then the one which requires less pressure, which has got lower stress, dominates, and the fracture doesn't grow into the other one. Just for information.
Okay. Well, actually, I also have another question for you, Carlo. So what you concluded right at the end is that if your ratio between essentially, imagine a situation when you have homogeneous formation, right? You have just ratio between vertical toughness and horizontal toughness, right? And so what you say that if this ratio exceeds square root of 2, right? So you have high vertical toughness, it means that fracture will be arrested. But say if you have homogeneous formation, you have homogeneous horizontal toughness, homogeneous vertical toughness, and vertical toughness is, say, 50% higher than horizontal toughness. What will happen? I mean, what will happen? I mean, I think you should have an elliptical fracture, right? But according to your analysis, you should have like a contained fracture, isn't it? I mean, what's the problem with this sort of assumptions or considerations?
Well, I would say that, so first of all, it's let's say this is the fact that the velocity vertical versus horizontal goes to 0. It's going to be asymptotically. It's going to be like not that you arrest, but your fracture will still slowly advance vertically and break through vertically slowly time by time. But then overall, the behavior that you would feel if you would be able actually to see the fracture growing from far, you will have the feeling that it's getting contained. And the rule and the assumption that you were saying, imagine a situation in which you have an homogeneous formation, but just that the toughness in the vertical direction compared to the one horizontally, the ratio is above square root of 2. Well, yes, this results may apply. Also, taking into account the fact, the limitation of the hypothesis that Danesi acknowledged. But you also have to consider that your dimensionless toughness needs to be sufficiently high to observe this thing to happen. And you also need to not to grow too much, because if your age start to be too large, then you hit the buoyancy land scale, and then the story changes.
Thank you. So we have one more question from comments by Colin, and so he said that you consider an analytical solution when hydraulic fracture just touches the interface, right? So essentially, I mean, again, you use fracture toughness, right? You have linear elastic fracture mechanics, but in reality, rocks, or the way the fracture propagates, that they have a fracture process zone, right? And so the question is, how would this process zone, right, or cohesive zone, if you wish, will affect your solution?
Yeah, that's another interesting point, and yeah, it goes along to the comments of Danesi before. Well, in this case, you for sure you will have what would I expect is that you will have a slowdown of the 8th growth. So this scenario that I assumed, where linear elastic fracture mechanics, actually the Young model is the same, and this makes the evaluation of the stress intensity factor at the interface actually much treatable, I would say. Well, this is an upper bound. So imagine all your fluid is there in the fracture, doesn't leak off. You don't consider that you have poor efficiency. And then all your fluid can propagate only vertically. And here we are asking, okay, what's the absolute? Imagine even these things of the presence of the bonding interface makes the fracture maybe turning as a T with a T shape. So in this case, really, this was trying the answer to answer this kind of question. Then the expectation for real problems where you have a different scenario, maybe that the time would be less. But again, I would like to see and to have some results with this kind of 3D simulations where you take into account also lateral propagation, because a lot of studies have been done in 2D plane strain, but then with this 3D, actually the novelty was to actually take into account of this transition timescale of propagating horizontal. Now, it would be very interesting to have some results or insights in the case in which you have some.
So Colin says here, so actually not an upper bound, because if you're moving into a layer with lower fracture toughness, then the process zone would zoom ahead. So it's not really an upper bound, I don't think.
Well, that's a very good point. So when you can have nucleation ahead, essentially. Yeah, that's true. We didn't account for that. So if I go back to this slide and I show you this plot here. Let's take one simple one here, and I show you the moment in which you propagate in the other layer here in the low toughness. Well, as you say, you're right. It could be that you have process zone advancing ahead. And it could be also in the linear elastic, in the small scale yielding approximation. It could be that you have nucleation ahead in the small layer. So yeah, these are interesting questions that needs to be addressed for a more complete answer. But anyway, once you reach the higher toughness, then we go back to the evaluation that I tried to make analytically before, and try to see, okay, do you arrest the fracture or not? Still assuming that you're running with a low speed fracture, okay, because this evaluation are also accounting for that, which is the case in most of hydraulic fracture propagation.
Also, I
guess industrial.
Going back to Ali Danish's point, though, if I have a horizontal well, the stress perturbation around the horizontal well could weaken some of the horizontal interfaces above it, and so as the fracture propagates up, then the shear stiffness of the interface could well be lowered. So I think it would be very good to include the possibility of T-shaping the propagation of fracture along the interface.
Yes, that would be very nice to have a more accurate. Yes, absolutely.
I think these are actually, I mean, excellent points, right? I mean, because your fracture can be arrested by stress layers, by toughness layers, by interfaces, by Young's modulus contrast, maybe by leak of layers, and so on. So there are actually many ways how fracture can be arrested, and then in this presentation we saw just one way of how, one mechanism out of many. I mean, and I think that's excellent that we discussed other possibilities. So do you have any more questions? I think we're done with the chat. Do you have any more questions from the audience? No, if not, let's thanks Carlo. Let me